So there are some situations in which we would like to explore completely the phase space, and we would like to also see the maximums and areas of the phase space that are rarely sampled if we follow the Boltzmann distribution and if we follow the Boltzmann probability density. We might want to do it in order to explore the conformational space of a molecule or of a system, or in order to explore the conformational space of a molecule or of a system with a very rugged and complex phase space, or we might want to do some free energy estimates, and in these cases we do also need to have a knowledge about places in the phase space that would be never or hardly ever explored with the normal dynamics. There are plenty of this kind of methods in order to do it. Today I'm going to introduce a large class of methods called non-boltzmann sampling. The name is quite self-explanatory. Instead of using the Boltzmann distribution and the probability of a state given by Boltzmann, we will use an alternative one. More precisely, what are we going to do? In this whole video I'm only going to consider the conformational phase space. So if we are doing a Monte Carlo, that's actually the whole phase space we're going to explore. If we're going to do a molecular dynamics, I am omitting all the parts relative to velocities, because they are not interesting in this situation. So remember, in molecular dynamics you have to add all the parts relative to the velocities or the momenta, as you would like to call them. If you are doing Monte Carlo, this is actually complete. So if we have some kind of potential, the Boltzmann distribution in a certain position, so the probability to have something in a certain position in space is e at minus beta v of r. Let's call it v0 to say that that's a standard potential, that's what we have, divided the conformational partition function, because we're only considering conformations. Otherwise, it would be the complete partition function. Now I'm considering it to be in the canonical ensemble, because otherwise in other ensembles it could look a little bit different. In canonical ensemble. And as we know, the partition function is actually, here we have the minus beta v0 a. The partition function is the a e at the minus beta v0 a. So that's our expression. Now we are going to use another weight, so another probability that we call in this way, in which we will add some kind of weight factor to what we already had. That's beta v0 a dr, our weight, e at minus beta v0 a. So that's what we got. We have put for what's for now an arbitrary weight factor, and we can choose this weight factor quite freely. The important thing is that we will be able to explore more the parts that we would usually not explore in a Boltzmann dynamics, and stay less time in the parts where you would pass 99% of the time if we use the Boltzmann density. So what we are interested in doing is, for example, if we have a system like this, in a Boltzmann dynamics, if we start here, we would probably stay here for the whole time and know only something about this path. If we started here, we will know only about this one, but we also want to know things about all these paths that would never be sampled or very rarely be sampled in a Boltzmann dynamics. And we want also, in some cases, to know the transition, to have some kind of transitions in order to observe them too. So we will have to choose this weight factor properly. But what is this weight factor in the end? Simple. Another way we can see this weight factor is by considering it as we are adding a bias potential to our system. So some kind of potential that will drag our system from one minimum to the other one, or will give it the possibility to explore high energy states. In fact, you will often hear that non-Boltzmann samplings add a bias potential, because that's how we can interpret this weight factor. So seen in this way, we will have that our weighted probability will be minus beta V0 plus divided of course all the potentials depend on R. This will be how we will express in this case our new probability of position R. So, and this is actually what is quite often done. It's not the only way in which you can express your weight factor. You can find an optimized weight factor written in any complex way you would like. You're not forced to write it in this way, but in the end you could always consider it as a bias potential. So for example, it could be that we have this very deep minimum, then this high barrier, and then a smaller minimum. We start here and we may add, for example, a completely random flat potential here, so that we won't have this minimum anymore. Our system will be here and we will have a bigger probability of also exploring this path and of also exploring the high energy path. That's the idea behind it. Of course, we will in the end need to re-get our Boltzmann probability, because that's the one that represents the real system we were interested in the beginning, and the formula is in the form of, and we can re-get it in this way. We'll have our modified probability divided the weight factor divided the ensemble average of the weight factor of 1 divided the weight factor in the weighted ensemble, so the one that we have created artificially. In this way we will be able to get the old probability. There are plenty of this kind of techniques, like for example there are the history independent ones like umbrella sampling, where you have to decide the weight factor at the beginning, so you must already know the right one, as long as we can talk about a right one. But of course it's not always easy to find which one is the right one, so there have also been developed some history dependent algorithms like the Wang-Landau method or method dynamics. I will talk about them in different videos, but in this one I wanted to introduce the general concept behind non-Boltzmann sampling. So as said, we are going to introduce a bias potential or some kind of bias weight factor in order to have a higher probability to explore different parts of the phase space that would usually not be explored or be explored very, very rarely with a standard molecular dynamics or a standard Monte Carlo. And as said, right here I only consider the configurational phase space, and this is absolutely correct if you're doing a Monte Carlo, but if you're doing molecular dynamics, of course you will also have the momentum part that you will simply have to add by a side, because it doesn't really have a huge impact on what you are doing. We are not going to higher the temperature by doing Boltzmann sampling or lowering it, even though the effect might be similar, but with Boltzmann sampling we are able to heat or cool only some selected degrees of freedom or a selected reaction coordinate by keeping the rest of the system absolutely normal. In this way we are not going to calculate how the system is at a very high temperature or very low temperature. We're going to calculate it at the temperature we're interested in, but we're going to heat or higher or lower the temperature, or simply giving a higher possibility to explore, or a lower possibility, if you're interested in the opposite, to explore the phase space of a certain degree of freedom or of a reaction coordinate, or it depends on your needs. So for example, if you have an dichloroethane, we know that we can have it in trans or in cheese. And if we would like simply to, we know that we can have them in both trans and cheese, and we could be interested in seeing the transition and try to get the transition rate. So we could put a weight factor that will give us the possibility to see this transition quite often without going to heat the other degrees of freedom, like the bending between the hydrogen and the chloride, without going to heat the stretching of any of these bonds, etc, etc, etc. The only thing I'm modifying is what I'm interested in. So in this case, the torsional degree of freedom of the double bond. And then of course I will be able to get the results in reality, so not in our modified system, with this formula. I hope you enjoyed the video. All the sources and the materials I used to do it are written in the description below. And here is some more content for you. But wait, don't click on it yet. First remember to leave a feedback in the comments section to let me know what you think about it. Like, subscribe, follow me on social media, links in the description. And if you would like to support the channel, consider to donate on Patreon. Again, link in the description below. See you next time. I'm Maurice Karnbrook for the Computational Chemist.